Here is a video for the second problem from your second free response quiz, which happens to be 2011, number 1. Alright, so we've got a projectile fired horizontally from a launching device, exiting with a speed v sub x. While the projectile is in the launching device, the impulse imparted to it is j sub p, and the average force on it is called force average. Assume that the force becomes 0 just as the projectile reaches the end of the launching device. And express your answers to parts A and B in terms of Vx, Jp, and force average. In part A, they want us to determine an expression for the time required for the projectile to travel the length of the launching device. Well, we know that impulse is equal to force times time, or the integral, but we can use, since they're talking about an average force here, we can use average force times time. Right? That's like the average value of the thing, so we don't have to do the integral since they gave us the average force. And that means that time is equal to Jp divided by average force. Part B, determine an expression for the mass of the projectile. Well, we also know about velocity, and we know that impulse is equal to change in momentum. Right? That's how we get the mass involved. So that means that impulse is equal to change in momentum. Well, its final velocity is Vx, and its initial velocity is 0, right? So that's the mv, right? So that means that m is equal to that. Right? I think your concept map should have helped a lot on those two, and those are worth 2 points apiece. Okay, now the projectile is fired horizontally into a block of wood that is clamped to a tabletop so that it cannot move. The projectile travels a distance d into the block before it stops. Express all algebraic answers to the following in terms of d, how far it travels, and the previously indicated stuff. So derive an expression for work done in stopping the projectile. Well, what's work equal to? Work is equal to, we could do force times distance, but we don't know the force, right? I think that's what we want to find afterwards. It's not the same force. It's not the average force from above. That was the force like on the thing as it was leaving the launcher. So I don't think that's going to work. So you might have gone in that direction, thought about that, but we don't know that. So the other way to go would be work is equal to the change in kinetic energy, and I think we can do that in terms of the variables that we have. So the work is equal to the change in kinetic energy. Its final kinetic energy is 0, right, because it's stuck in the block, it stops moving, minus its initial kinetic energy, which is 1/2 m v squared, right? That's its initial. And then we're not supposed to have an m in here. That's not one of our variables, but we have an expression for it right here. So that means work is equal to -1/2 Jp over Vx times Vx squared. And one of the Vx's will cancel out there, giving us -1/2 Jp times Vx. That's the work done. Right? Notice that that's equal to its initial kinetic energy. That's going to be important later on. And you got, I think, 2 out of 3 points if you got this, but you didn't have the negative sign. You do need to understand that the block is doing negative work, right? Because this is coming in and it's losing potential energy, so that's negative work. All right, part D. Derive an expression for the average force exerted on the projectile as it comes to rest in the block. Well, the average force times distance would be equal to work, right? Just like we used here, this is very much analogous to what we did here. If you know if this is an average force or the force is constant, you can use force times distance. So that means this force is equal to work, which we just found. That was negative 1/2 Jp times Vx over d. That's all there is to that. So again, I guess one of the things we want to take from this, if you didn't get these parts, is that when you're given an average force, you can treat that in much the same way that you would treat a constant force. Right? It makes calculations a little simpler, and it circumvents having to do integrals. All right, now a new projectile and block are used identical to the first ones, but the block is not clamped to the table. So we're going to fire it in and the block's going to slide. That sounds like momentum, doesn't it? The projectile is again fired into the block of wood and travels a new distance d into the wood block while the block slides across the table a short distance d. All right, assume the following. The projectile enters the block with the same velocity. Average force has the same value determined in part D. So we know the average force here. And the average force of friction between the table and the block is Ft, another average force. And the collision is instantaneous so that the frictional force is negligible during the collision. All right, so derive an expression for dn, that's how far the block slides. No, I'm sorry. That's how far it slides in, like here, right here. That's how far it goes into the block, in terms of d, ft, and fb as appropriate. Okay, well, let's think about what's going on here. This is an energy problem again. I know that the change in kinetic energy is equal to the work done. But there's two things doing work now. There's the work done by the block, and there's work done by friction. Right? That's the difference. Here, we just had the work done by the block. Or sorry, I should be pointing to here. We just said this is just the work done by the block. So this time we've got two things doing work. So let's see if we can plug some stuff in here and figure out what's what. So I know that this, the change in kinetic energy, is, let's see, they don't want me to have Jp in there. So let me see if I can figure out what that kinetic energy, let's see, so the initial kinetic energy, this is the connection we want to make here. This work done right here, they said that the work is the same, so that means the work done here and the work done here are the same. So this is another expression for the change in kinetic energy. Right, because these two things are equal to each other. So here I can substitute that, right? And the work done by the block is now how it's the force, that average force on the block, but it's the new distance dn, right? Because the dart is only sliding in this smaller distance dn now, right? But it's the same average force. Plus, the force of friction is the frictional force, which they told us is F sub t, for table, I guess, times that distance, which is it slides across the table a short distance d. Right. So we need to solve this for, aren't we trying to solve for this, right? So d sub n is equal to, I will spare you the algebra. It's equal to this. So that was a little tricky, and I think, to my mind anyway, that's the trickiest part, substituting an expression for the kinetic energy, realizing that work is equal to the change in kinetic energy, and they said that that would be the same, right? It's the change in kinetic energy is the same. It's still losing all of its kinetic energy, so it's still equal to that. All right, last part, F. We've got, now they want us to derive an expression in terms of d, the mass of the projectile. Sorry, derive an expression for this in terms of d, the mass of the projectile, and the mass m of the block. And the masses there might put you in mind, since we haven't done the conservation of momentum yet, that we want to do that. So let me get a little bit more paper here for this last part. So let's see, part F. We have conservation of momentum. So the mass of the dart times its initial velocity is going to be equal to the two masses together plus that velocity there immediately after the collision. Right? And solving that for v, we get m Vx over m plus m. Right? Now we also know that the kinetic energy, this is the kinetic energy of the block with the dart stuck in it immediately after the collision. Right? That kinetic energy is equal to the work done to stop the block. Right? Work equals change in kinetic energy. This is an idea that we've used lots of times, that the amount of work it takes to stop something is equal to its kinetic energy. Right? And what's the force that's stopping the whole block configuration from moving? It's the friction, right? The friction of the table. So this is that frictional force times that distance. And we can substitute this in now. M Vx plus m squared. And we're supposed to be finding an expression for, what are we supposed to be solving for here? We are supposed to be solving for, where did it go? For dn, which is how far the block slid, how far the block goes in the second time. Right? Well, let's just do a little simplifying here first. So I got 1/2. One of those cancels out. I still have an m plus m on the bottom. M squared Vx squared equal to g times d. Right? And if you rearrange things a little bit here, you can get 1/2 m Vx squared, and then you have an m over m plus m. And that's the initial kinetic energy of the dart, right? And we know that that initial kinetic energy of the dart is equal to, just like we substituted in the last problem, that's equal to the force of the first time and that distance the first time. Right? We have that from earlier. So that's a really crazy trick there. And you actually, you got the full 2 points for the problem if you got, what is it? If you got to this right here. If you got this far, you got the full 2 points for this part. So I think they recognized that this was maybe harder than they meant for it to be. But making that substitution here, and then you can solve for D in terms of the variables that they wanted. So, oh no, is there still another substitution? I guess you still have to make some other substitutions. And I'll let you try to figure that out, and you can look at the rubric, which I'm looking at right here off to the side if you want to see more of what to do. But you get something like that in the end. That was a hard problem, but keep in mind they gave the 2 full points, one for this and one for getting this far. So you didn't have to do all that craziness to get the full credit.